I would like to introduce Kevan Shaw, who has spent his entire career in lighting. He worked in stage lighting through his 20s and early 30s. He established Kevan Shaw Lighting Design as an architectural lighting design practice in 1989, and he remains a consultant to them. He is a board member of the International Association of Lighting Designers and leader of the European Regulatory Affairs Working Group. He's a member of CEN standards work groups, and he has received numerous awards, including the Lux Lighting Designer of the Year Award, a LIT Lifetime Achievement Award, and election to the IALD College of Fellows, amongst others. And he developed a strong interest in non-visual effects of light and has led the group writing the IALD white paper on integrative lighting. And he's lectured for university master's courses on lighting and frequently presents at conferences. So I will stop sharing and then let him take over.
Hi, thank you for that, Lisa. Really interesting paper, really showing a practical application of what I'm about to start talking about. It's the white paper is really to help practitioners in lighting and lighting design understand what's needed and how to make lighting work for non-visual aspects of light. We're not aiming to mimic biological lighting. It's not really possible with electric light. What we're trying to do is to identify things that will certainly minimize potential harm, because we are aware that inappropriate light at inappropriate times can cause problems, but also to maximize the benefits, which are visible in sleep areas and potentially in other areas as well. We need to move on from marketing jargon that surfaced around this topic as human-centric lighting. What we have called the paper is integrative lighting. It provides more accuracy and acknowledges that we're looking to make a holistic approach to lighting. So we're incorporating not just the visual approach that we normally have, but also these non-visual aspects of light. This has been defined properly in this CIE paper in 2018. And this is the definition on the screen here. Really, it's about getting everything right. So when we start looking at the system and what's happening here, this graph shows relative sensitivity of human photoreceptors in relation to daylight. And this is what we are going to come on to talk about as the standards and measures that we're using for this now. We can see here, if you look at the blue curve, which is the effective melanopic light, against the yellow curve, which is the standard white light, CIE V lambda function, and the definition of the lumen, it starts to introduce a metrics dilemma. Basically, if we're optimizing for the lumen, then we're neglecting and reducing the frequencies of light that are most important for these, the IPR, GC particularly, and other non-visual lighting effects. So it creates a metrics dilemma, because it appears that by providing this additional light that you're actually making light less efficient. It's just we're not measuring the right thing. So how do we measure it? What has become the standard is the melanopic equivalent daylight illuminance. So what we again defined in CIE 026 2018, it makes a balance or measurement between what light you're experiencing and the amount of it that is effective. And it's related to daylight on the basis that daylight is obviously the correct and most effective light for humans, one way and another. Oops. Sorry, I've suddenly lost my screen. Nope. Something has gone wrong at this end. Can you still see my screen?
Yes.
All right, okay. Okay, I think it's got back now. Sorry about that. Some weird technical problem. Um, so right, sorry. Just momentarily lost track with this. So essentially the melanopic EDI allows you to determine a measure, which we're calling melanopic lux, that allows you to quantify potential benefits and impacts on the biological aspect of light. One thing that we have to bear in mind when we're looking at biological aspects, we're measuring these vertically at the eye, not horizontally, as is the practice for everything else to do with lighting. We've also achieved research consensus on the quantities of melanopic lux, MEDI, that are required to ensure proper entrainment. This comes from a paper that was published again in 2017, and the numbers are 250 melanopic EDI lux during daytime to achieve entrainment. In the evening, we need to go below 10 melanopic EDI lux at least 3 hours before bedtime, and 1 melanopic EDI lux during sleep periods. These aren't absolute rigid requirements, but they're thresholds. The 250 is a bottom threshold, and the 10 and the 1 are upper thresholds. The other thing that has to be remembered is that these have been derived from research, as usual with lighting and most other things, that's been done around students. So they're typically for a 32-year-old eyes. Obviously, older populations might need higher levels due to reduced light transmission through aging lenses, and the very young need much less because of the more transparency in their eyes. So the limited research in the area of the aging eye suggests there's not a straightforward numerical relationship between reduced transmission of the eye and melanopic effect. This is an active area, so one we need to think about but be careful about. How do we figure out these things? Well, there's a CIE S026 toolbox spreadsheet. It's available online. These are 2 screenshots from it, which allow you to calculate MEDI values from spectral power distribution data for any given light source. Our manufacturers should increasingly provide MEDR values that allow you to work these things out. This tool helps when that information isn't available. What you do is you input spectral power distribution, either given from the manufacturers of the LEDs or from measurements with a spectrophotometer that you might have made or can make. When you input it into what you see at the left-hand side of the spreadsheet, on the right-hand side, you get the output equal effect of the light source in this area. Now, when we were researching the white paper, one of the most interesting new developments involves infrared and near-infrared spectrum. This is the other end from the IPR-GC effective end. Again, the infrared and near-infrared were considered wasteful in lighting energy efficiency because they don't add much to your V lambda curve, so that they're not good for the lumen. However, infrared and near-infrared affect the entire body, and they penetrate through clothing and can get deep into the body depending on the wavelength and intensity. This raises important questions about our transition from incandescent sources, which were naturally rich in infrared, to LEDs, which typically don't have any at all. Are we potentially overlooking a beneficial wavelengths in pursuit of apparent efficiency? So research by Glenn Jeffrey, Rob Fosbury, and others suggests that infrared and near-infrared wavelengths influence mitochondrial function. Mitochondria are parts of cells that convert nutrients to cellular energy, and they play critical roles in cell signaling and metabolism. Studies at the moment indicate that appropriate infrared and near-infrared exposure may support mitochondrial health and potentially affect everything from cognitive function to tissue repairs. Our research is still developing, but it represents a new frontier in understanding of light's biological impacts. So the graph on the left shows a bit what we've lost from infrared in the transition to LED lighting. Traditional incandescent sources produce significant IR content, shown in red, while LEDs typically produce none. Similarly, with glazing, increasingly infrared rejecting coatings have been applied to reduce solar gain and heat gain in the summer and reduce heat loss from heating systems in the winter. So the environmental reduction in IR indoors may be significant in reducing biological effects. So I'm not here suggesting that we abandon energy-efficient technology, but we should consider whether supplemental infrared may be beneficial in certain applications and for certain populations. We need to watch research in this area as it matures. And I gather beginning of next year, we should see a couple of papers come out on this subject where research is now being done for infrared in the normal lit environment. Previous papers have largely been relating to medical interventions by using infrared and near infrared. So thinking about technological considerations, flicker, temporal lighting artifacts present particularly challenges with LED lighting. The requirement to provide DC current at voltage much lower than mains voltage necessitates some amount of electronics. Typically, what is done is you rectify the AC and reduce the voltage. Again, this is typically done across the board, and particularly in lighting now, by pulse width modulation. So what you're doing effectively is switching LEDs on and off very quickly. If the switch rate is too low, because the LED goes from full on to full off, this can become visible either as flicker or create stroboscopic effects, including what's known as the phantom array. That's also an interesting aspect of the eye, because those appear when the eye scans across a light source, a bit like the image at the top here. Became very popular with car tail lights a while back. The thing is that these effects are not always perceptible to the conscious mind. Research has shown that the frequencies that can be experienced are much, much higher than had been thought when we were originally talking about using high frequency to reduce apparent flicker. So it needs to be thought about, because inappropriate flicker, inappropriate temporal lighting artifacts can cause headaches, eye strain, trigger seizures in several individuals, and flicker of any sort seems to be particularly problematic for neurodivergent people. Another aspect that has been brought up with the advent of LEDs is photobiological safety. There was much talk about the blue light hazard, and initially concern was justified. However, with current developed marketplace, the major concerns have been eliminated through better understanding and better technology in producing light from blue LEDs. Properly designed general lighting poses minimal risk. However, there are certain conditions that can occur with lighting that can increase these dangers, specifically magnification of light sources or failure of protective phosphors. By magnification, it's the same thing as you would not use any kind of magnifying thing to look at the sun. So any intense blue light source magnifying things, or potentially intense blue light source, any magnifying things can cause risk of damage to the eye. And in terms of protective phosphors, what we have seen at times is the protective phosphor, or the phosphor which creates white light from blue light, can fall off. Again, not so much these days, but certainly in early days of LEDs, and now older generations of LEDs are beginning to fail in this way, and you get color shifts. But those color shifts are the result of blue being directly exposed and therefore blue exposure increasing. Right now, products that should comply with EN 62471 and meet a risk group of 1 or 2 classification. Also remember that young children under 2 and again, people suffering from certain medical conditions have special sensitivity and require additional cautions. So existing product developments are beginning to use UV and violet pumped LEDs instead of blue. As wavelength decreases, the risk of inappropriate emissions becomes greater. We all know that intense ultraviolet is particularly damaging, hence some protection from arc welding and such like electrical discharges. So we need to be aware where we start to see violet and UV pumping, that if that gets loose for whatever reason, that is potentially going to be a risk. The other area of future concern is laser LEDs. Currently, these are turning up in specialist applications such as projection, stage lighting, and such like. Currently, the lasers are typically used to excite phosphors rather than being directly emitted. So as long as they comply with the ICN IRP guidelines and EN 62741, these will be safe in normal use. However, the risk of retinal damage from direct laser exposure is very high. So any situation that comes up that potentially allows lasers to get out there is really bad and to be avoided. So back to integrative lighting. This is something that has been developed after the paper. It's a sort of flowchart to talk about integrative lighting design. What it generally shows is there's not much change from your normal lighting design practice, except maybe some further consideration of things or more detailed consideration of things. Like we need to be more clear about user demographics, understanding age groups, visual acuity needs, and sensitivities brought about by age of one sort or another. We need to know more about user activities in the space, understand the tasks, concentration needs, and visual demands. We need to analyze timing of space use, the impact in terms of circadian entrainment changes according to time of day. So we need to know where people are at what time of day to understand whether there's a lighting requirement to improve the non-visual impacts. We need to assess environmental factors. Again, we would do that normally, but maybe just with a different slant to what you're thinking of. Looking for windows, orientation, daylight obstruction, and impacts of seasonality. We also need to look at existing lighting conditions, the current light levels, spectrum and controls, particularly when you're looking at a retrofit kind of solution. And then we need to make decision as to whether enhanced non-visual lighting is required as part of what we're doing. So if not, we can just go into the normal process. But if we do want to do this, we need to set the targets for non-visual lighting according to the standards that we've spoken about. And we need to more carefully document the non-visual aspects of the metrics so that we can take those into the lighting design process, which then just takes account of the additional requirements as well as the visual requirements. So it's not much different from what you do normally, just a little different accent. And I think it's important to think about these things as we're going through a design process. So we must remember again, repeating myself a bit, but it's really important when we're dealing with lighting of this nature. We must remember that not everyone experiences light the same way. Age is significant. There is the issue, as I said before, of eye transmittance, though this is not straightforward and there's ongoing research. Neurodivergency is a bigger issue about lighting in general, particularly when it comes to brightness, glare, flicker, and such like. And then you have some outlying cases like night shift workers. Now, when you come to consider them, and this is a really difficult question, are you going to either protect them from shifts of diurnal behavior, or are we going to reinforce the shifted time that they are in order to accomplish their tasks when they're working? That is again a big area that there's plenty of room for research and understanding and thought, very much about how people need to have light and how people would need to have any particular non-visual enhancement to their lighting according to their diurnal rhythms that they're actually living in. So integrative lighting is increasingly recognized as a valuable consideration in lighting design, but the uptake of it in lighting standards and documentation and recommendations has lagged behind a bit. Currently, the standards addressing integrative lighting include the Wellbeing standard and DIN TS 67600. Currently, work's going to incorporate some of the WELL standards into the BREEAM, the Building Research Establishment Environmental Assessment methods, and other similar things that you find in other countries in the Middle East and in America. So when it comes to the WELL standard, what they have done is they've incorporated two tiers of approach or recommendation. The first tier now falls below what is accepted required values to have effective melanopic impact. The second tier values do meet the expected standards, basically 250 melanopic EDI, or a considerable amount of additional daylight in the spaces. So the problem with this is that there may be problems achieving that second tier standard when you take into account the requirements for LO4, which looks for a glare rating of UGR 19 or better. As you are needing to deliver significant lighting levels at the eye, managing that within a glare requirement is quite challenging. So the DIN TS 67600 provides much more comprehensive guidance, very much in line with what we're talking about. It describes the design process and maintenance requirements. It restates the CIE SO 26/2018 definitions of integrative lighting and the associated recommendations and metrics. It also recommends monitoring of the complete installation after 1 year to get effective user feedback. Now, this is going to be vital to ensure any system to provide integrative lighting and to have non-visual effects is actually meeting those design goals, and it's going to help recording and research and enhancing recommendations over the next many years. I mean, these standards are both voluntary, but can be increasingly influential as they get incorporated in setting project requirements. They become things that are asked for in the design brief. Subsequent to publication of the paper, ISO CIE 8995-1 2025, Light and Lighting for Workplaces, Part 1 was published. There's very much a restating of EN 12464-1, which is the European standard for workplace lighting. However, it's later, That was last published in 2019, and it's incorporating sections on integrative lighting. It also goes on in an annex to give further detail and restate the requirements that we've been talking about before, the 250 lux at the eye during the day, no more than 10 in the evening, and no more than 1 overnight. So it's very much in line, but this is not going to be applied everywhere. Pardon the external sounds. So what else is going on? Currently, CN TC169 work groups 2 and 13 are looking at how to incorporate non-visual effects of light into the European standards. I'm on this work group, and we met in June and September this year, and are going to try and produce a technical standard which will be published hopefully in about 2 years' time, which will provide a foundation for incorporating non-visual effects of lighting in the next review of EN 12464-1, which isn't going to be published until sometime between 2029 and 2031. So it's a ways off, and this interim guidance is going to allow a better approach and better information for people trying to incorporate integrative lighting into general lighting schemes. So there are challenges with implementing these things. Energy codes and compliance has already been discussed, that we're not working with the lumen, and the lumen is the base numeric for assessing lighting energy use. Budget constraints is an issue. It is always perceived that this kind of lighting is going to cost more. Maybe not. It's a case-by-case thing. Balancing competing lighting objectives, that's going to be, things more to do with aesthetics and issues maybe about glare or brightness, apparent brightness. Those need to be balanced with everything else. So to address these, we need to include strategies such as emphasizing daylight integration to reduce electric lighting needs. Thinking about how we actually apply a melanopic lighting system, make sure it's applied only in key areas where people spend time rather than cover entire buildings. There's very little point in providing complicated and expensive lighting systems in areas where people are only there in transit. Corridors, staircases, and the like do not need this kind of thing, whereas dwell areas do. These systems require time-based controls, providing higher lighting levels only when most beneficial. It's a key part to managing energy use when it comes to melanopic lighting. And the most important thing is engaging with clients, establishing the value proposition of health supporting lighting. And there's many discussions about how important it is in an operating building that you look after your people, because they are much, much higher cost to you in terms of wages and everything else than any other cost to do with the building itself. So quality of light remains subjective. It has to encompass both the measurable and experiential factors. True lighting quality includes appropriate illumination, good color rendering, proper distribution, temporal stability, biological appropriateness, and emotional response. All have to be contextually appropriate to the particular space, function, and the users in it. We've got to remember our entire evolution has developed through outdoor living as hunter-gatherers in agrarian societies right up until the early 19th century. Given that in the last 2 centuries we've changed to a predominantly indoor industrial society, we have to consider that our physical beings are not significantly moved on in our relationship with light. So we don't evolve in the space of 200 years. We evolve in the space of 200,000 years. So we need to bear in mind that if we're going to spend all day indoors in artificial light, we need to manage that light so that it produces the best solution, or we go out. So as a species predominantly meant to live outdoors in daylight and indoors, or at least protected, hopefully beside a nice, warm, incandescent, infrared-rich fire at night, these conditions of relatively bright, high-color temperature in the day while we work and low brightness, warm, incandescent lighting at night when we relax and sleep are our natural condition. As professional lighting designers need to approach projects considering integrative lighting with knowledge and with care. We need to be fully informed, communicate clearly the benefits and risks of specific lighting interventions to health and well-being. Our primary goal is to minimize potential harm to people in the environments we design. We need to understand the population we are specifically designing for and be aware of the different requirements for different groups. Research is forever taking us forward. We've discussed current work in near-infrared impacts on mitochondria. This has the potential for further impacts on designing for well-being in the foreseeable future. Finally, what we've discussed is only mitigation of the reality we spend most of our lives in relatively dim, predominantly electrically LED-lit indoor environments, rather than under the natural light out of doors. We can improve the electrically lit environment to an extent, and can advocate for better access to daylight indoors and more opportunity to spend time outdoors in nature. We cannot duplicate or replace natural light and shouldn't pretend that we can. So this is a QR link to directly download the IALD paper. Please do read it and share it with your colleagues. And I must give a huge thanks to all the members of the work group, both the IALD members and volunteers, and a special thanks to Roger Sexton, Virginie and Majiki, and the other members of the Good Light group who pushed IALD to update this paper and contributed much information and advice. As lighting design professionals, we should always research and work with the user at the center of our design. We have and should keep a key role and saying on where things should be going and when in terms of research and lighting design in the future. Thank you.